Hello and welcome. This is the team project demonstration video presented by Eric Kiefer, Torsten Bergersen, Brian Lamb, and George Vourvopoulos. We're excited to showcase our work on the microcontroller home humidity sensor. I'll start off with a fun sales pitch introduction for our project and then transition to discuss our project highlights before passing to my teammates to discuss their individual roles on the project. Meet your home's new sixth sense for comfort. Think of this as your home's personal comfort meter. We designed it to instantly tell you if your air is too dry, too humid, or just right. No guesswork required. A small sensor quietly measures your room conditions, the screens show the exact numbers, and a color-changing light gives you an instant visual cue. Even the brightness can be adjusted with the touch of a button. Whether you're caring for plants, protecting electronics, or just keeping your space cozy, one quick glance tells you everything you need to know. For our project, we developed a real-time environmental monitoring system that combines precise readings with simple visual cues. At its core, we have the Raspberry Pi Pico microcontroller, which then gathers temperature and humidity from the DHT20 sensor. This information is shown on a 16:2 LCD for exact numbers, while the WS2812B LED strip instantly signals whether conditions are ideal, borderline, or extreme. A button lets users quickly adjust LED brightness, making the system adaptable to different lighting conditions. We developed our software in MicroPython using the Thony IDE, with a focus on modular design, user-friendly interaction, and strong error handling to keep the system accurate and dependable. On the left side, you'll see our breadboard setup, the earliest stages where we connected the microcontroller, sensor, display, LED strip, and button. This gave us easy access to wiring changes and rapid testing. On the right is our prototype enclosure, a compact, organized version ready for real-world use. All components are securely mounted and is designed for a clean, user-friendly appearance. From the user's perspective, the LCD shows real-time humidity and temperature readings for decision-making, while the LED strip provides an instant at-a-glance status. The adjustable brightness button improves usability, and built-in error alerts keep readings trustworthy. We approached testing in 4 phases. First, we verified each hardware component on its own. Second, we integrated them and checked for conflicts. And then third, we stress tested the system with edge cases and simulated errors. Finally, we ran full system validation over extended periods. We developed a UML diagram, mapped our program structure, showing how each function, input and output connected. This visual guide made it easier to coordinate across the team, debug efficiently, and confirm that every part worked together as intended. At this time, I'm going to pass to each team member who will describe their portion of the project.
Hello, my name is Eric Kiefer. I'm going to share my contribution to the project, which was largely hardware related. My first task was to test each individual component. This involved writing a short script, wiring that component to the Pico, compiling, downloading the files, and then documenting the findings. The next step was putting everything together, making sure that the electrical and power needs were met by each component, and documenting, which is what this diagram represents the final configuration. Next, I handled or was coming up with a way to handle button presses. With one of the pins connected to ground, the button push caused a pin to change voltage, and that would we wanted that one push to result in one event. However, there's a phenomenon called chatter that occurs when pushing a button in that fashion, and I wrote some code to eliminate the phantom events. Next, I needed to tie that button press with a hardware interrupt. This is code that fires immediately upon an event, no matter where the program is logically. For instance, in our program, we had a main while loop, and that to allow for program execution outside that loop, we needed the interrupt to fire and then come and allow us to update a variable that ultimately adjusted the brightness level for LED array. After that was coming up with a durable prototype, something that you could just plug in into your house, your home, and would not be fragile. And I first purchased an enclosure and started cutting into it to make such prototype, and realized this is a lot more difficult than it looks. Cutting plastic is challenging. It melts as you cut it with a saw. Straight lines are hard to make. Components need to be fastened. Tape and glue wasn't working, and I needed a way to prevent the wires from pulling out. That led me to the second version, which is shown on this slide. This relied heavily on screws, screw terminals, fastening things with screws. In order to attach components to the enclosure, I needed to first solder them onto small circuit boards. And then I had holes from that circuit board that I could attach the components to. And then I also needed to come up with a way to have the USB micro extend through the case so that a user didn't have to open up the case every time they needed to disconnect or connect the sensor. Lastly, I was involved in coming up with a program to simultaneously log events to a file and to the console. And this was a little bit challenging because the Pico had limited resources, and the version of MicroPython that we were using didn't have all of the same libraries that a normal version of Python would have. Ultimately, we came up with a way to do that. And that was my major contribution to the project.
Hello, my name is Torsten, and I was responsible for the firmware on this project. So everything that runs on the Pico, I focused on two main files, main.py, which controls the system loop, and sensor interface.py, which handles communication with the humidity sensor. My job was to make sure the Pico could reliably read data, display it, drive the LEDs, and respond to user input, all while keeping things stable and efficient. We used MicroPython running on the Pico and wrote all the code in the Thonny IDE. I think this was the right choice for rapid development and easy debugging. The firmware is modular, so sensor interface handles the I2C communication with the DHT20 sensor, while main.py maps those humidity readings to LED patterns and LCD messages. Everything was designed to be non-blocking and interrupt-driven, so the system could stay responsive even while sleeping between updates. Development was broken up into three main phases. First, I set up the environment and tested the I2C communication. In phase 2, I built the control loop and humidity to LED logic. The third phase focused on error handling, things like CRC checks, fail-safes, and how the system reacts if a component disconnects. And finally, I cleaned up the code and wrote some inline documentation, altogether spending about 100 hours on a firmware design and refinement. Some challenges and lessons. Probably the biggest challenge I ran into was a dead sensor initially. So during that first phase, I had to simulate fake readings so we could continue development and testing. Once I got a working one, I swapped it in and fine-tuned the logic I had created prior. I also added hystereses to prevent the LEDs from flickering when the humidity hovered near a boundary. So basically creating a buffer zone so it wouldn't rapidly switch back and forth. Overall, I learned a lot about embedded development and how important it is to test on real hardware as early as possible. Thank you.
Hi, this is Brian Lamb. I was the display lead for our project. So with this project, we used the provided 8 LED strip. However, only 6 of those were used. You can see that we have an array pattern example on the right of what colors should be appearing based on the humidity level. Each of the LEDs can be individually addressable with any RGB colors, and the library used for this project was NeoPixel to control the LEDs. The functions for this LED driver includes clear LED, which clears the LED strip of any colors, LED array, which displays LEDs based on the color and the number of LEDs to exhibit, and flash LED, which flash 6 red LEDs a set amount of times, which is controlled by the user. I was also in charge of creating the LCD interface. This controls the 16x2 LCD module that we have. It contains a configuration to set up the 16x2 cells. Each of these cells consists of 5x8 dot matrix, which is communicated through I2C. The library we used for this one was Pico I2C LCD. And the functions that it provides is clear LCD, which clears the LCD display, and display LCD, which displays a given string to the LCD display. I was also responsible for setting up the brightness control of the LEDs via the button. So for this integration, each button press would alter the brightness level, and the button would be able to interrupt when pressed. We've integrated it into the display LEDs function in main, and I also fixed the color definitions that we defined by the brightness value set by button.py. In summary, some challenges that we faced were different time zones and schedules. We never met in real time, but we used Discord to communicate with each other. We also had some overlapping activities that resulted pivot to new responsibilities. So for example, I created the installation video as well as some hardware docs with specs. As for what I've learned throughout this project, I learned how to work with the Raspberry Pi Pico. And then this is kind of my first big project where we developed something in a larger group setting. And then I also learned how I could improve my skills as a developer as well.
Hello, my name is George Vourvopoulos. For this project, my primary role was the test lead, while also contributing to the documentation side. My main focus was ensuring that each hardware and software component performed reliably across normal and edge conditions. I created a structured 4-phase test plan, starting from basic hardware validation, moving through integration testing, and then ending with long-duration stress and regression tests. On the technical side, I developed MicroPython scripts to drive functional testing of the LCD display, LEDs, button input, and the DHT20 humidity and temperature sensor. We chose MicroPython because it gave us quick iteration cycles on the Pico and allowed us to easily interact with the I2C devices and addressable LEDs. The combination of NeoPixel LEDs and I2C LCD in the DHT20 sensor gave us a clear way to visually communicate sensor readings and system states. Our original plan was straightforward, to build separate modules for the LCD, LED buttons, and sensor, then integrate them into the main loop with proper error handling. Some of the issues arose, however, when we skipped the pseudocode step early on, which delayed testing for me because many modules had to be finished before the integration could begin. That experience kind of reinforced how important upfront planning is for us to enable parallel development. As we progressed, I focused on integration testing and later introduced fault injection testing in Phase 3. This allowed me to simulate sensor failures without physically unplugging any of the hardware. One of the biggest challenges was hardware timing, particularly button debounce and ensuring the I2C sensor was ready before each read. To solve this, I built modular test scripts to debug components individually and created targeted edge cases for humidity thresholds and sensor error handling. This project reinforced for me how critical the modular design is for hardware and software integration. By separating out the components into testable modules, we caught issues much earlier than if we had tested the full system at the end. We also learned the value of pacing our tests. In physical systems, adding deliberate delays helps confirm behavior visually, which is something that you don't think about in a pure software project. On the team process side, the absence of early pseudocode planning really showed us how quickly small planning gaps can cause delays downstream. Personally, I came away from this project with stronger skills in MicroPython, particularly working with the I2C devices and NeoPixel LEDs. I gained experience in designing edge cases and fault injection tests, which I'll carry forward into future embedded projects. Lastly, this project was just generally fun. Throughout this program, done a lot of projects, and particularly the fact that there was this hardware integration that I could show my kids and have some fun, like pushing a button and changing lights. That was really enjoyable for me as I developed through my career in computer science. So for some next steps, a lot of us had lots of opportunity to use this product in our home to test humidity and actually keep our homes at the desired temperature and humidity. So this did improve our health, and then for me personally, it helped with some of the humidity here in Florida. We will post some of our findings on our social media accounts. So how can we improve this project in the future? So we can add Wi-Fi for remote access. We can expand on some of the sensors, adding some different information about the air quality, and then we can go further into our 3D printed enclosure, improving the visual prototype. You can find us here at this link for our GitHub. And with that, I would just like to thank everyone